Welcome. Tonight, we're going to explore the fascinating history of the steam engine. A story that unfolds slowly across centuries, with the gentle rhythm of pistons and the soft hiss of steam. Let yourself relax as we journey through time, discovering how humanity learned to harness the power of water turned to vapor. Our story begins not with a sudden invention, but with ancient observations. Long before anyone thought to build an engine, people noticed that steam has power. The ancient Greeks, in their temples and workshops, saw steam rising from heated water. They watched it lift lids from pots. They felt its warmth. Around 50 AD, a mathematician named Hero of Alexandria created a simple device called an eolipile. It was a hollow sphere that could spin when steam escaped from bent tubes attached to it. It was a toy, really. A curiosity. Nobody thought to use it for work. But it showed that steam could create motion. For more than 1500 years after Hero's invention, steam remained a curiosity. The world ran on muscle power, on water wheels, on windmills. People burned wood and coal for heat, but they didn't yet understand how to turn that heat into useful mechanical work in any systematic way. The knowledge lay dormant, waiting. In the 16th and 17th centuries, European thinkers began to study air and gases more carefully. They discovered that air has weight, that it exerts pressure. In 1606, the Italian Giovanni Battista della Porta described a device that used steam pressure to raise water. In 1629, another Italian engineer, Giovanni Branca, described a wheel turned by a jet of steam striking blades. These were ideas on paper, sketches in notebooks. The practical steam engine was still waiting to be born. The real beginning of our story comes in the late 17th century in England, where a problem needed solving. Deep mines, especially coal mines and tin mines, filled with water. Miners could only dig so deep before groundwater made further work impossible. Pumping this water out by hand or by horses was exhausting and expensive. Someone needed to find a better way. In 1698, Thomas Savery, an English military engineer and inventor, patented what he called the miner's friend. It was the first practical steam-powered device for pumping water. Savery's engine had no moving parts like pistons. Instead, it worked by creating a vacuum. Steam would fill a chamber, then cold water would be poured over the outside of the chamber, condensing the steam inside and creating a vacuum. This vacuum would suck water up from the mine. Then more steam would push that water higher up and out. It was ingenious in its simplicity. But Savery's engine had problems. It could only raise water about 20 or 30 feet. The steam pressures required to lift water higher were dangerous with the metalworking technology of the time. Boilers could explode. The engine consumed enormous amounts of coal. Still, it was a beginning. It showed that steam could do useful work. Around the same time, a French physicist named Denis Papin was experimenting with steam in a different way. In 1690, he had invented the pressure cooker, which led him to understand how steam pressure could be contained and controlled. In 1698, he designed an engine that used a piston. Steam would push a piston up, then the steam would be condensed, creating a vacuum that pulled the piston back down. Papin's ideas were brilliant, but he never built a full-scale working engine. His design remained theoretical, another stepping stone. The next great step forward came from Thomas Newcomen, an ironmonger and lay preacher from Dartmouth, England. Around 1712, working with his assistant John Caille, Newcomen created what became the first practical and widely used steam engine. Newcomen almost certainly knew of Savory's work and perhaps Papin's ideas. He combined and improved upon them. Newcomen's engine used a large cylinder with a piston inside. A heavy beam balanced on a central pivot point, like a seesaw. One end of the beam connected to the piston, the other to a pump rod that went down into the mine. Steam from a boiler would fill the cylinder, pushing the piston up. Then cold water would spray into the cylinder, condensing the steam and creating a partial vacuum. Atmospheric pressure, the weight of the air itself, would then push the piston back down. This downstroke provided the power to pump water from the mine. It was called an atmospheric engine because it was really atmospheric pressure, not steam pressure, that did the main work. The beam rocked back and forth, up and down, with a slow, steady rhythm. You could hear these engines from a distance, a regular creaking and hissing, breathing like some mechanical creature. Each stroke took several seconds. The pace was gentle, almost meditative. Newcomen's engines spread across England and Europe throughout the 18th century. They were large, heavy machines housed in substantial brick buildings. They consumed vast amounts of coal, but in coal mines, fuel was cheap and readily available. By 1733, there were more than 100 Newcomen engines operating. By 1775, there were hundreds more. They pumped water from mines, allowing deeper and deeper excavation. They enabled the coal industry to expand, and coal would fuel the industrial revolution that was coming. These engines were tended by enginemen who learned their rhythms and quirks. Each engine had its own personality, its own sounds. The enginemen would listen to the hiss of steam, the splash of injection water, the creak of the great wooden beam. They could tell when something wasn't quite right. It was skilled work, this partnership between human and machine. But Newcomen's engine, remarkable as it was, wasted most of its energy. The cylinder had to be heated with steam, then cooled with water, then heated again with each cycle. All that heating and cooling consumed fuel. For 70 years, this was simply accepted as the nature of steam engines. Then came James Watt, a young instrument maker at the University of Glasgow, what was given a model of a Newcomen engine to repair in the winter of 1763 and 1764. As he worked on it, he began to think deeply about how it functioned and where it wasted heat. During a walk on a Sunday afternoon in May 1765, the solution came to him in a flash of insight. Why heat and cool the same cylinder over and over? Why not keep the cylinder always hot and condense the steam somewhere else? This idea, simple once you see it, was revolutionary. Watt designed a separate condenser, a chamber apart from the main cylinder where the steam could be condensed. The cylinder could stay hot. The condenser could stay cold. This change dramatically reduced fuel consumption, making the engine 3 or 4 times more efficient than Newcomen's design. But having an idea and making it work are different things. Watt needed precision metalworking beyond what was commonly available. He needed money to develop his invention. He needed time. In 1769, he received a patent for the separate condenser. But developing a working full-scale engine took years of frustration. Watt formed a partnership with an industrialist named Matthew Boulton in 1775. Boulton had the resources and the business acumen. Together, they would change the world. By 1776, the first Boulton and Watt engines were operating. They were better than Newcomen engines in every way. More efficient, more reliable, more powerful. The partnership thrived. Watt continued inventing improvements. In 1781, he patented a sun and planet gear system that converted the engine's back and forth motion into rotary motion, allowing the engine to turn wheels and drive machinery. This meant steam engines were no longer limited to pumping. They could power mills, factories, anything that needed a turning shaft. In 1782, Watt patented the double-acting engine, where steam pushed the piston both up and down rather than relying on atmospheric pressure for one stroke. This doubled the engine's power. He invented the parallel motion linkage, an elegant mechanical solution to guide the piston rod in a straight line. He invented the centrifugal governor, a device that automatically regulated the engine's speed using spinning weights. When the engine ran too fast, the weights flew outward and closed a valve, slowing it down. When it ran too slowly, the weights dropped and opened the valve again. It was automatic, self-regulating, one of the first examples of feedback control in machinery. These Boulton and Watt engines spread throughout Britain's growing industries. Cotton mills used them to spin thread and weave cloth. Flour mills used them to grind grain. Breweries used them to stir and pump. The engines were leased rather than sold, with Boulton and Watt charging a portion of the coal savings compared to older engines. It was a clever business model, and it made both men wealthy. Watt himself was a perfectionist, a worrier, sometimes melancholy. He wrote letters filled with technical details and personal anxieties. But his engineering was superb. The engines that bore his name were marvels of precision. The boring mills that created their cylinders, developed by John Wilkinson, could create cylinders accurate to within the thickness of a thin coin. This precision was essential. Steam had to be contained. Pistons had to fit snugly. There was no room for sloppiness. By the turn of the 19th century, as Watt's patents began to expire, others were free to experiment with new designs. A Cornish engineer named Richard Trevithick began working with high-pressure steam. Watt had always used steam at just slightly above atmospheric pressure, partly for safety reasons. Trevithick was bolder. He built strong boilers that could withstand much higher pressures. High-pressure steam meant smaller, lighter engines with more power. It also meant greater danger. Boiler explosions could and did kill people. But Trevithick pushed forward. In 1801, Trevithick built a steam-powered carriage that carried passengers on the roads of Cornwall. It was the first self-propelled vehicle to carry passengers successfully. In 1804, he built a steam locomotive that ran on rails at an ironworks in Wales, pulling 10 tons of iron and 70 men in 5 wagons. The age of steam transportation had begun, though it would take another 2 decades before steam railways became practical. The development of the steam locomotive is a story that unfolded gradually through the early 19th century. Trevithick's early locomotives were too heavy for the cast iron rails of the time, which often broke under their weight. But the idea had been planted. In mining areas, horses pulled wagons along wooden and iron rails. Could steam engines replace those horses? George Stephenson, the son of a colliery fireman in Northumberland, became fascinated with steam engines as a young man. He taught himself to read as an adult, studying by candlelight after long days of work. He learned engineering through hands-on experience, taking apart and reassembling engines, understanding how they worked through touch and observation. In 1814, he built his first locomotive, called Blucher, for hauling coal at the colliery where he worked. It could pull 8 loaded wagons at about 4 miles per hour. Not fast, but faster and more tireless than horses. Stephenson continued improving his designs. In 1821, he was appointed engineer for the Stockton and Darlington Railway, which opened in 1825. It was the first public railway to use steam locomotives, though it also still used horses for some trains. The real breakthrough came with the Liverpool and Manchester Railway, which opened in 1830. Stephenson and his son Robert designed the locomotives for this line. The railway was entirely powered by steam engines from the beginning. It carried both freight and passengers. It ran on a published schedule. It was, in many ways, the first modern railway. For the opening of the Liverpool and Manchester Railway, there was a competition at Rainhill to choose the best locomotive design. Stephenson's locomotive, named Rocket, won decisively. It incorporated several advanced features, including a multi-tube boiler that increased the heating surface area, making the engine more efficient. Rocket could reach speeds of up to 30 miles per hour, an astonishing velocity that seemed almost magical to people accustomed to the pace of horses. The success of the Liverpool and Manchester Railway sparked railway mania. Within a few decades, railways spread across Britain, Europe, and North America. They shrank distances. Cities that had been days apart by coach were now hours apart by train. Fresh food could travel from the countryside to cities. News and mail moved faster. People of modest means could travel distances that had once been possible only for the wealthy. The world was speeding up, knit together by iron rails and the rhythmic chuffing of steam locomotives. Meanwhile, steam power was also conquering water. Steamboats had been experimented with since the late 18th century. In 1787, John Fitch operated a steamboat on the Delaware River in America. In 1807, Robert Fulton's steamboat Claremont made a successful journey up the Hudson River from New York to Albany, proving that steam-powered river transport was commercially viable. Steamboats soon plied rivers and coastal waters, their paddle wheels churning, their smokestacks trailing coal smoke. Crossing oceans with steam was more challenging. Early steam engines were too inefficient and steamships had to carry so much coal that there was little room for cargo or passengers. Sailing ships remained faster and more economical for long ocean voyages. But engines improved. In 1838, 2 steamships, the Sirius and the Great Western, raced across the Atlantic. Both succeeded, proving that transatlantic steam travel was possible. The Great Western, designed by the brilliant engineer Isambard Kingdom Brunel, was the larger and faster of the 2. Brunel went on to design even larger steamships. The Great Britain, launched in 1843, was the first iron-hulled, screw-propeller-driven ship to cross the Atlantic. The Great Eastern, launched in 1858, was enormous, nearly 700 feet long, far larger than any ship built before. She could carry 4,000 passengers and enough coal to steam to Australia without refueling. The Great Eastern was perhaps too ambitious for her time, and she was not a commercial success, but she demonstrated what steam power could achieve. By the mid-19th century, steam engines were everywhere in industrialized countries. They powered factories, mines, railways, ships. They drove pumps, looms, saws, hammers, printing presses. The rhythmic thump and hiss of steam engines became the soundtrack of industrial life. Factory districts were landscapes of tall brick chimneys pouring coal smoke into the sky. The air smelled of sulfur and soot. Rivers ran discolored with industrial waste. Progress had a price. Engineers continued to refine steam engine designs. The compound engine, which expanded steam through 2 or more cylinders in succession, extracted more work from each unit of steam and saved fuel. The triple expansion engine, developed in the 1880s, used 3 cylinders of increasing size, allowing the steam to expand in stages. This made steamships much more efficient and economical. The great ocean liners of the late 19th and early 20th centuries used triple expansion engines and later even more complex designs. The reciprocating steam engine, with its pistons moving back and forth, was a triumph of mechanical engineering. But it had limitations. The back and forth motion created vibration. The engine had many moving parts that wore and needed maintenance. Engineers dreamed of a simpler, smoother way to extract power from steam. The answer was the steam turbine, invented independently by several engineers in the late 19th century. The most successful was designed by Charles Parsons in 1884. Instead of pushing a piston back and forth, steam in a turbine flows continuously over blades mounted on a rotor, spinning them at very high speed. It's like a windmill, but powered by jets of steam instead of wind. The motion is smooth and continuous. There are fewer moving parts. Turbines can be much more powerful than reciprocating engines of the same size. Parsons demonstrated his turbine dramatically in 1897. He had built a small turbine-powered boat called Turbinia, capable of speeds up to 34 knots, faster than any vessel afloat. At the Spithead Naval Review that year, where the British fleet was assembled for the Queen's Diamond Jubilee, Turbinia raced among the warships at high speed, easily outrunning the patrol boats sent to chase her away. It was a spectacular demonstration. Navies took notice. Within a few years, turbines were powering warships. Turbines also revolutionized electricity generation. In the late 19th century, power stations began using steam engines to turn generators, producing electricity that could be transmitted through wires to light streets and homes. Turbines were ideal for this purpose. They could run at the high speeds that generators needed, and they could be built in enormous sizes. By the early 20th century, large steam turbines were the heart of power stations around the world, a role they still play today. Steam locomotives continued to develop through the late 19th and early 20th centuries, becoming larger, faster, and more sophisticated. The great express locomotives of this era were magnificent machines, gleaming with polished metal and paint. Their names became famous: the Flying Scotsman, the Mallard, the 20th Century Limited. In 1938, the Mallard set a world speed record for steam locomotives, reaching 126 miles per hour on a stretch of track in England. That record still stands. But even as steam locomotives reached their peak of development, their replacement was already appearing. Diesel engines and electric motors, more efficient and cleaner, began to take over rail transport in the mid-20th century. By the 1960s, most developed countries had phased out steam locomotives, though they lingered longer in some places. In China and parts of Africa, steam locomotives were still being built and used into the 1980s. Today, steam locomotives survive mainly as heritage attractions, lovingly maintained and operated for enthusiasts and tourists, living reminders of an earlier age. Steamships too faced competition and obsolescence. Diesel engines and turbines burning oil instead of coal became standard for ships in the mid-20th century. The last major passenger liners powered by coal-fired steam engines were retired in the 1960s and 1970s. Nuclear-powered vessels, which use the heat from nuclear reactors to create steam, represent a specialized continuation of steam power in some naval vessels and icebreakers, but they are rare and highly specialized. In industry, steam engines for power generation and mechanical drive were gradually replaced through the 20th century by electric motors and internal combustion engines, which were more convenient, efficient, and cleaner. By the late 20th century, the reciprocating steam engine had largely vanished from everyday use, except in a few specialized applications and in developing countries where older technology persisted. And yet steam power has not disappeared. Most electricity in the world today is still generated by steam turbines. They are just hidden away in power plants, humming quietly in vast buildings, spinning at thousands of revolutions per minute. Coal-fired power plants burn coal to boil water and create steam. Nuclear power plants use nuclear reactions to create heat that boils water into steam. Even some solar thermal plants use mirrors to concentrate sunlight, heating fluid to create steam. In each case, the steam drives turbines that turn generators, producing the electricity that flows through the wires to our homes and devices. The steam engine, then, never really went away. It transformed, evolved, became hidden. The visible, clanking, hissing steam engines of the 19th century, with their great wheels and connecting rods, their plumes of steam and trails of smoke, have mostly vanished into museums and heritage railways. But the principle remains as important as ever. We still boil water to make steam. We still use that steam to turn turbines. The steam engine, in its modern form, is still the heart of industrial civilization. Reflecting on this long history, we can see a pattern. Innovation happened slowly, building on previous work. Savory built on observations about steam and vacuum. Newcomen improved Savory's design. What improved Newcomen's? Trevithick pushed beyond Watt's caution. Stephenson and others refined Trevithick's ideas. Each generation of engineers learned from and built upon the work of those before. The steam engine also shows how technology and society shape each other. The need to pump water from mines drove the development of early steam engines. Those engines enabled deeper mining, producing more coal. More coal fueled more steam engines, which powered factories, which produced goods more cheaply, which changed how people lived and worked. Railways shrank distances and connected markets. Steamships opened oceans to regular traffic. The world became more connected, more industrial, more urban. There were costs. Coal mining was dangerous work. Factory labor was often harsh and poorly paid. Air and water pollution from burning coal damaged health and environment. The wealth generated by industrial steam power was unevenly distributed, enriching some while others toiled in difficult conditions. The social upheavals of the industrial age, from urban overcrowding to labor movements, were intimately connected to the spread of steam power. But there were also remarkable benefits. Material prosperity increased, though unequally. Transportation became faster and more accessible. Communication sped up. Goods that had once been luxuries became common. Innovations in one field spilled over into others. The precision metalworking developed for steam engines enabled better machine tools, which enabled other technologies. The organizational methods developed to run railways influenced business management broadly. The people who created the steam age were diverse. Some, like Watt and Brunel, were trained engineers and natural philosophers. Others, like Stephenson and Trevithick, were largely self-taught, learning through hands-on work. Some were wealthy industrialists. Others started with nothing and rose through talent and determination. Their work was not always recognized in their lifetimes. Many innovations came from small improvements by workers and craftsmen whose names were never recorded. There is something fundamentally human about the steam engine. It takes the ancient human practice of making fire and extends it, harnesses it, turns it into controlled mechanical power. Water and fire, two primal elements, are brought together. The result is motion, work, power. There's an elemental poetry to it. The sound of a steam engine is distinctive. The chuff of a locomotive, the rhythm of a beam engine, the high-speed whisper of a turbine. Steam itself is dramatic, visible and invisible at once, wisps of white vapor that appear and vanish. The heat and pressure are real, tangible, dangerous. You can be burned by steam, scalded by hot water. Early engine men and stokers knew this intimately. Their work had physical risks and required constant attention. Maintaining a steam engine required skill and knowledge passed down through apprenticeship and experience. You learned by watching someone who knew, by making mistakes, by developing a feel for the machine. You learned to recognize sounds that meant something was wrong, to notice changes in rhythm or pressure. You learned when to oil, when to tighten, when to back off. It was craft knowledge, embodied knowledge, not easily written down in books. The age of visible steam power, of engines you could see and touch and hear working, lasted roughly from 1700 to 1950, 250 years. A significant span in human terms, but a blink in the longer scope of history. Before steam engines, human and animal muscles, water wheels, and windmills were the primary sources of power beyond human scale. After steam engines came electricity, internal combustion, jet engines, nuclear power. Each transition was complex and gradual, with old and new overlapping for decades. When we think of the Industrial Revolution, We often focus on Britain in the late 18th and early 19th centuries. But industrialization spread unevenly around the world. Belgium, France, Germany, and the United States industrialized through the 19th century. Japan industrialized rapidly in the late 19th century. Russia pursued industrialization in the late 19th and early 20th centuries. China's industrialization came mainly in the late 20th century. The steam engine was part of different stories in different places, adapted to local needs and conditions. In some places, steam technology arrived as part of colonial imposition. Railways in India, Africa, and other colonized regions were built primarily to extract resources and move troops, though they also enabled new forms of commerce and communication. The great steam engines of the British Empire connected colonies to imperial centers, part of networks of power and exploitation. This legacy is complex, neither simply good nor simply bad, but certainly consequential. The environmental legacy of the steam age is still with us. Centuries of burning coal released carbon dioxide into the atmosphere, beginning the increase in greenhouse gases that drives climate change today. The coal-fired power plants that still generate much of the world's electricity continue this pattern. The transition away from fossil fuels is, in a sense, the task of moving beyond the steam age's reliance on burning coal and oil, even as we continue to use steam itself in turbines powered by nuclear or renewable heat sources. But let's return to the machines themselves, because there is a beauty in their engineering. Consider the elegant solution of Watt's parallel motion linkage. 3 bars arranged so that a point on the middle bar moves in a nearly straight line even though the bars pivot and swing. Watt called it one of his proudest inventions, even though it seems like a small thing. But it solved a real problem gracefully. Or consider the compound engine, with its high-pressure and low-pressure cylinders working in series, extracting more work from the expanding steam at each stage. It's conceptually simple. Don't waste the pressure that remains after the first expansion. But implementing it required precise machining, careful design, good understanding of thermodynamics. The result was an engine that used fuel more efficiently, making long-distance steam shipping economical. Or consider a triple expansion marine engine in a great ocean liner, its 3 cylinders of increasing size, its massive crankshaft turning smoothly, driving the propeller shaft through reduction gears. The whole assembly is a marvel of coordination, thousands of pounds of steel moving with precision, hour after hour, day after day, crossing oceans. Engineers and stokers tended these engines constantly during voyages, making small adjustments, ensuring everything ran smoothly. The heat of the engine room, the noise, the smell of hot oil and coal smoke, the vibration underfoot as the engine turns, these were the sensory reality of steam power. It was hot, dirty, sometimes dangerous work. But there was also pride in keeping a great engine running well, in understanding its moods and quirks, in being part of the skilled crew that made the machine work. Imagine standing in the engine room of a steamship at night, watching the play of light and shadow on the moving parts, feeling the deck move slightly with the sea, hearing the steady rhythm of the engine. There's a meditative quality to it, the repetition, the reliability, the sense of controlled power. The engine breathes, in a way, inhaling steam, exhaling motion. Steam locomotives, too, have this quality. The sound of a steam locomotive working hard, climbing a grade, is distinctive. The sharp exhaust beats, rapid and forceful, the chuff 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 that comes from steam being released from the cylinders after each power stroke. The rhythm changes with the engine's speed and the load it's pulling. Engine men learned to hear what the locomotive was telling them through these sounds. The smell of coal smoke and hot oil, the radiant heat from the firebox, the slight sway and rock of the locomotive's motion, the view ahead down the rails, these were the experiences of the footplate crew, the driver and firemen who operated the locomotive. The fireman's job was to keep the fire burning right and the boiler full of water, shoveling coal into the firebox, monitoring gauges, working in intense heat. The driver controlled the throttle and brakes, judging speeds and distances, watching for signals. It was teamwork, and it required skill and constant attention. When a steam locomotive stands still, building steam before departure, you can watch the safety valves lift slightly, releasing excess pressure with a soft hiss. Steam wisps upward and disappears. The engine is breathing, waiting. Then the driver opens the throttle, and steam rushes into the cylinders. The driving wheels begin to turn, slowly at first, sometimes slipping if the rails are slick. The exhaust beat begins, slow and heavy, then quickening as the locomotive gathers speed. There's a moment where you can feel the transition from stillness to motion, the awakening of power. Stationary steam engines, the kind that powered factories and mills, have their own character. A great beam engine, the kind Newcomen and Watt built, rocks up and down with ponderous dignity. Each stroke takes several seconds. You can watch the whole cycle: steam admitted, expansion, condensation, the beam swinging down, then up again. It's hypnotic. Some of these engines ran for over 100 years, day and night, with occasional stops for maintenance. They were built to last, made of massive timbers and iron, designed when durability was paramount. The engine house for a beam engine is often a beautiful building, proportioned to accommodate the tall engine. Brick walls, large windows to let in light, a high ceiling to give clearance for the beam's arc. Some engine houses are architecturally distinguished, built with pride to house important machinery. They still stand in places, sometimes with their engines preserved inside, monuments to the steam age. Smaller steam engines, the kind that powered individual machines or workshops, were more common but less celebrated. A small horizontal engine, a few horsepower, might drive the line shafting in a workshop from which individual machines could be belted. These little engines were simple and robust. They could run for hours unattended if properly set up. Many workshops and small factories had their own steam plant, a boiler, an engine, perhaps a small coal bunker. It was local, independent power. The transition to electric power changed this. Instead of each factory having its own steam engine and boiler, factories could buy electricity from a central power station and use electric motors to drive machinery. This was cleaner, more convenient, and often cheaper. The factory didn't need to employ stokers and engine men. The transition happened gradually through the early 20th century. Old steam plants were shut down, dismantled. The era of distributed steam power gave way to centralized electricity generation. But again, the central power stations themselves use steam, just at a much larger scale and in a different form. The turbines and boilers in a power station are descendants of Newcomen's engine and Watt's improvements. The principle is the same. Burn fuel to boil water, use the steam's energy to do mechanical work, which is then converted to electricity. The chain of causation runs directly from the early steam engines to the power plants of today. It's worth pausing to consider the thermodynamics of steam engines, the science that explains why they work. Heat flows from hot to cold. A steam engine takes heat from a hot source, the fire or boiler, converts some of that heat to mechanical work, and rejects the rest to a cold sink, the condenser or the atmosphere. The maximum efficiency of this process is limited by the temperature difference between the hot source and the cold sink. This is the second law of thermodynamics, first articulated clearly in the mid-19th century by scientists studying steam engines. Sadi Carnot, a French engineer, published a paper in 1824 analyzing the efficiency of heat engines. Carnot imagined an ideal engine, perfectly efficient within the limits set by nature. Real engines fall short of this ideal, but Carnot's work showed that there were fundamental limits to efficiency that no clever engineering could overcome. You can't get more work out of a heat engine than the temperature difference allows. This insight helped establish thermodynamics as a science. Rudolf Clausius and William Thomson, Lord Kelvin, developed these ideas further in the mid-19th century, formulating the laws of thermodynamics clearly. The study of steam engines led directly to fundamental insights about energy, heat, and entropy. The practical need to build better engines drove theoretical understanding, and that understanding in turn enabled better engine design. It's a beautiful example of how technology and science advance together. The efficiency of real steam engines improved dramatically from Newcomen's time to the 20th century. Newcomen's engines were perhaps 1 or 2% efficient, meaning only 1 or 2% of the heat from the burning fuel was converted to useful work. Watt's separate condenser and other improvements raised efficiency to perhaps 5% or more. High-pressure engines and compound designs pushed higher. By the early 20th century, the best triple expansion engines might reach 15% efficiency. Steam turbines in modern power plants can exceed 40% efficiency, approaching the theoretical limits for their operating temperatures. Each percentage point of efficiency gained meant less fuel burned for the same amount of work. In an age when fuel had to be dug from the ground, transported, and burned, efficiency mattered economically. It also mattered environmentally, though people in the 18th and 19th centuries didn't think in those terms. Less fuel burned meant less smoke and pollution, though this was rarely a primary consideration. Coal mining, which fed the steam age, was brutal work. Miners descended into dark, cramped, often wet tunnels. They cut coal with picks and shovels, loaded it into carts, hauled it to the surface. Cave-ins, floods, explosions, and toxic gases killed thousands. The steam engines that pumped water from the mines and lifted coal to the surface enabled deeper, more productive mines. This increased both the wealth produced and the risks borne by miners. Labor movements in the 19th century often centered on coal miners and industrial workers, fighting for better wages, shorter hours, safer conditions. The Toll-Puddle martyrs, the Chartists, the early trade unions, these movements arose in the steam age, responding to the conditions of industrial labor. The steam engine didn't just change technology, It changed society, creating new classes of workers and new forms of social conflict and organization. Cities grew explosively during the Steam Age. People moved from the countryside to work in factories. Urban populations surged. Housing was often inadequate, crowded, unsanitary. Diseases spread in slums. Smoke from thousands of coal fires, domestic and industrial, darkened the air. In London, thick fogs mixed with coal smoke created the infamous pea soupers, smog so thick you could barely see across the street. These conditions drove public health reforms, sanitation improvements, eventually clean air legislation. Railways and steamships also changed patterns of migration and trade. Irish fleeing famine in the 1840s crossed the Atlantic on steamships to America. Europeans migrated to America, Australia, South Africa in huge numbers, enabled by cheap steamship passage. Goods moved in volumes and at speeds previously unimaginable. Refrigerated steam ships brought meat from Argentina and Australia to European tables. The world's economies became interconnected in new ways. Steam technology also had military implications. Steam-powered warships replaced sailing warships in the mid-19th century. The first battle between ironclad steam warships, the Monitor and the Merrimac in the American Civil War in 1862, showed that wooden sailing warships were obsolete. Navies raced to build more powerful steam-powered battleships. Railways moved armies and supplies faster than ever before, changing military strategy. The American Civil War, the Franco-Prussian War, and the world wars of the 20th century were all shaped by steam-powered transportation. The steam-powered printing press, invented in the early 19th century, made books and newspapers cheaper and more widely available. Literacy increased. Information spread faster. The steam-powered press could print thousands of sheets per hour, far more than hand-operated presses. This helped create mass media and public education systems. Ideas, like goods and people, moved faster in the steam age. Think about the experience of traveling in the early 19th century versus the late 19th century. In 1800, traveling from London to Edinburgh took several days by stagecoach, bouncing over rough roads, stopping frequently to change horses. The journey was expensive, uncomfortable, often dangerous. By 1850, you could take a train and make the same journey in less than a day, sitting in a heated carriage, watching the countryside roll by at 40 miles per hour. The cost was a fraction of the coach fare. Middle-class people could travel for business or pleasure in ways that had been impossible for their grandparents. This expansion of mobility and communication created new possibilities but also new anxieties. The world seemed to be speeding up. Traditional ways of life were disrupted. Rural communities lost population to cities. Skilled artisans found their crafts mechanized, their expertise devalued. Not everyone welcomed the changes that steam power brought. There were Luddite rebellions in England in the early 1810s, where textile workers destroyed the machines they feared would take their jobs. The fear was understandable, even if the response was ultimately futile. Change continued regardless. By the late 19th century, steam power had created a world that would have been almost unrecognizable to someone from a century earlier. Cities were larger and more industrial. Railways crisscrossed continents. Steamships crossed oceans on regular schedules. Telegraph wires, often following railway lines, carried messages instantaneously across vast distances. The pace of life had accelerated. Yet for all the changes, much of human life remained recognizably similar. People still lived in families, worked to support themselves, hoped for better futures for their children. The steam engine changed what kinds of work were available and where people did that work, but it didn't change fundamental human needs and desires. People adapted to the new technologies, incorporated them into their lives, made them familiar. The sounds and sights of steam became part of everyday experience in industrial areas. The whistle of a locomotive became a time signal, letting people know when trains were departing or arriving. Factory whistles, powered by steam, signaled the start and end of work shifts. The rhythmic sounds of engines became background noise in industrial neighborhoods, so constant that people stopped consciously hearing them. Children grew up with steam technology as a normal part of life. Boys, especially, were often fascinated by locomotives and steamships. Model trains became popular toys. Engineering became a prestigious profession, attracting talented young people. The great engineers of the steam age, people like Brunel and Stephenson, were celebrated as heroes, their achievements widely known. Women's roles in the steam age were complex. Women worked in factories, often in textile mills powered by steam engines. The work was hard and poorly paid, but it offered some economic independence. Middle-class women rarely worked directly with steam technology, but their lives were changed by it. Railways made travel easier, steamships enabled emigration or visits to distant family, steam-powered machinery produced cheaper cloth and other goods. Some women, like Ada Lovelace, engaged with the cutting edge of mechanical and computational thinking, though they were rare exceptions in male-dominated fields. The aesthetic of steam technology influenced art and architecture. The Crystal Palace, built for the Great Exhibition of 1851 in London, was a massive structure of iron and glass, showcasing Britain's industrial achievements. Steam-powered machinery filled the exhibition halls. Millions visited, marveling at the products of the steam age. The building itself, though not powered by steam, was made possible by the iron industry that steam engines enabled. Victorian engineering had a characteristic aesthetic: heavy, solid, often ornate. Railway stations were built like cathedrals, with grand arched roofs supported by iron trusses. Bridges were massive stone and iron structures. Steamships had elegant lines and often elaborate decoration. There was pride in the work, a sense that these engines and structures were not just functional but beautiful. Some steam engines were literally works of art. Showman's engines, used to power fairground rides and generate electricity for lighting, were often decorated with polished brass, painted panels, and elaborate detailing. They were meant to impress, to attract attention. Their owners took great pride in their appearance. Even today, restored Showman's engines appear at heritage events, gleaming in the sun, their paintwork pristine. Traction engines, steam-powered vehicles that could haul heavy loads or power threshing machines and other agricultural equipment, were common in farming areas in the late 19th and early 20th centuries. They moved slowly along roads, puffing smoke, their large wheels crushing the road surface. Some were fitted with living quarters, as their crews would travel from farm to farm, spending days or weeks at each location during harvest season. Steam rollers, heavy engines used for road construction, were another familiar sight well into the 20th century. They moved even more slowly than traction engines, their massive rollers compressing road surfaces. The work was hot and dirty, but necessary. Many roads we drive on today were first compacted by steam rollers a century ago. Steam-powered cranes lifted heavy loads in ports and construction sites. Steam hammers forged large iron and steel parts. Steam shovels excavated earth for railways, canals, and foundations. The variety of steam-powered machinery was enormous. If heavy work needed doing, someone had probably designed a steam engine to do it. In agriculture, steam power enabled mechanization on a large scale. Steam-powered threshing machines could process grain much faster than hand threshing. Steam plows could turn heavy soil. Though tractors with internal combustion engines eventually replaced steam in agriculture, there was a period of several decades when steam traction engines were common on farms, particularly in North America and Britain. The coal that fed all these engines came from ever deeper mines. Mining technology advanced alongside steam technology. Better pumps allowed deeper shafts. Steam-powered hoists lifted coal to the surface. Steam-powered ventilation fans circulated air through the workings. Railways, often narrow gauge, transported coal underground. The coal mine itself became a complex industrial system centered around steam power. The dangers of mining led to innovations in safety. The Davy lamp, invented by Humphrey Davy in 1815, allowed miners to detect methane gas without igniting it. Steam-powered fans reduced the buildup of dangerous gases. Stronger timber and later steel supports reduced the risk of cave-ins. But mining remained dangerous. Explosions and accidents killed hundreds or thousands of miners each year in the major coal-producing countries. The coal miners who fed the engines, the stokers who tended the boilers, the engine men who operated the machinery, these workers were essential to the steam age. Their labor, often hard and dangerous, powered industrial civilization. Labor movements grew strong among these workers, organizing for better pay and conditions. Strikes in coal mines or on railways could paralyze whole regions, demonstrating the workers' collective power. Governments gradually intervened to regulate working conditions, restrict child labor, improve safety. These reforms were hard-won, often coming only after disasters or prolonged struggles. The steam age forced societies to grapple with questions of workers' rights, industrial safety, and the role of government in regulating business. The environmental impact of the steam age was mostly local and immediate. Smoke-darkened buildings, polluted rivers, deforested hillsides where timber was cut for mine supports or fuel. The broader atmospheric impact of burning fossil fuels wouldn't be understood until the 20th century. People in the 19th century knew coal smoke was unpleasant and unhealthy, but they didn't know it was changing the global climate. Forests were cut to feed early steam engines before coal became the dominant fuel. In some regions, deforestation from industrial demand caused soil erosion and changed local climates. But coal was so abundant and energy-dense that it quickly became the preferred fuel. Britain had vast coal reserves. So did parts of America and Europe. This abundance of coal enabled the steam age to expand rapidly. The geology of coal is itself a story. Coal forms from ancient plant material, compressed and chemically altered over millions of years. Different types of coal, from lignite to anthracite, have different burning characteristics. Coal seams, the layers of coal underground, vary in thickness and quality. Miners learned to read the rock to understand which seams were worth working. Extracting coal from deep underground and transporting it to where it was needed was a massive logistical challenge. Canals were built to move coal by barge. Railways were often built primarily to transport coal. Ports specialized in coal export developed, like Cardiff in Wales and Newcastle in England. Carrying coals to Newcastle became a proverbial expression for a pointless activity because Newcastle had so much coal already. The business of coal mining created fortunes for mine owners and investors. It also created powerful companies that dominated regions economically and politically. Company towns, where the mining company owned the houses, shops, and even the currency, were common. Workers were dependent on the company for everything. This created a kind of economic feudalism that persisted well into the 20th century in some areas. The culture of mining communities was distinct. Mining was hereditary in many families. Sons followed fathers into the pits. There was pride in the skill and courage required. There was also a strong sense of solidarity born from shared danger. Mining communities had their own songs, traditions, and forms of mutual support. The steam engine brought these communities into existence, creating demand for coal that only deep mining could satisfy. And the steam engines served these communities, pumping water, lifting coal, providing the power that made deep mining possible. It was a self-reinforcing cycle. Steam engines enabled more coal production, which enabled more steam engines. This cycle continued through the 19th and early 20th centuries, reaching its peak around 1910 to 1920. Then, gradually, other energy sources began to compete. Oil and natural gas, easier to transport and cleaner to burn, began replacing coal in many applications. Hydroelectric power, using water turbines instead of steam turbines, provided electricity without burning fuel. Nuclear power, which generates heat through atomic reactions rather than combustion, eventually powered some steam turbines. The decline of steam was gradual and uneven. In Britain, steam locomotives were phased out rapidly in the 1960s. In America, the transition happened earlier, in the 1950s. In parts of Asia and Africa, steam lingered longer. The last commercial steam locomotives in regular service operated in China until the early 2000s. Some industrial steam engines continued to operate until quite recently in specialized applications. Today, working steam engines are mostly found in museums, heritage railways, and special events. Enthusiasts restore and maintain them, keeping the knowledge and skills alive. Steam rallies bring together traction engines, showman's engines, and other steam-powered equipment. The machines are demonstrated, put through their paces, shown to new generations who may never have seen steam power in everyday use. There's something moving about these preservation efforts. The people involved are keeping history alive, maintaining a tangible connection to the past. When you watch a steam locomotive in operation, properly maintained and skillfully handled, you're seeing technology exactly as it was a century or more ago. The locomotive doesn't know it's in a museum. It works the same way it always did. The smell of coal smoke and hot oil, the sound of the exhaust, the sight of steam rising, these sensory experiences connect us directly to the past. People who work with preserved steam engines often speak of a special feeling, a connection to history, to the engineers and workers who built and operated these machines when they were new and at the cutting edge. Some preserved steam railways operate regular services, carrying passengers on scenic routes. Riding a steam train today is a tourist experience, a step back in time. The pace is slower than modern transport, which is part of the appeal. You can watch the countryside go by, hear the locomotive working, feel the slight sway and rocking of the carriages. It's a different way of traveling, more contemplative. There are also operational steam-powered boats and ships, maintained by enthusiasts or operating as tourist attractions. A few steam-powered fairground rides still operate at traditional fairs. Industrial heritage sites preserve steam engines in their original settings, sometimes demonstrating them for visitors. These living museums help people understand what the steam age was really like. The educational value is significant. Seeing a steam engine operate makes the technology understandable in a way that diagrams and descriptions cannot. You can see the piston moving, see the connecting rod turning the wheel, see steam escaping. It's visible, tangible physics and engineering. Many people who became engineers cite seeing steam locomotives or engines as a formative childhood experience. As we near the end of our journey through steam engine history, it's worth reflecting on what this technology means. The steam engine was one of humanity's great innovations, arguably the innovation that launched the modern industrial world. It showed that heat could be systematically converted to mechanical work. It provided power on a scale previously impossible. It enabled the factories, railways, and ships that transformed the 19th century. But the steam engine was also a product of human ingenuity building over time. No single person invented it. Savery, Newcomen, Watt, Trevithick, Stephenson, and countless others each contributed pieces. Workers and craftsmen whose names we don't know made crucial improvements and solved practical problems. The steam engine emerged from a collective process of innovation spanning centuries. This reminds us that technology is a human creation, shaped by human needs and choices. The steam engine developed the way it did because of the specific problems people were trying to solve: pumping water from mines, powering machinery, moving goods and people. Different problems would have led to different technologies. The path wasn't inevitable. The steam engine also reminds us that technologies have consequences beyond their intended purposes. The inventors of steam engines wanted to solve specific mechanical problems. They probably didn't foresee all the social changes their invention would enable: the growth of cities, the rise of factory labor, the acceleration of transportation, the transformation of warfare, the integration of global trade. Technologies reshape society in ways that are hard to predict. Today, we're in the midst of new technological transformations: digital technology, artificial intelligence, biotechnology, renewable energy. Like the steam age, these changes bring both opportunities and challenges. Understanding the history of the steam engine might help us navigate our own era of change. We can ask, who benefits from new technologies? What are the environmental costs? How do we ensure that progress benefits everyone, not just a fortunate few? How do we preserve what's valuable from the past while embracing beneficial change? The steam engine's legacy is all around us, even though most steam engines are gone. The railways it created still operate, though with different power sources. The factories it powered still exist, though they now use electric motors. The global trade networks it helped establish still connect economies. The scientific understanding it spurred, particularly in thermodynamics, remains fundamental. The steam turbines in power plants still generate much of the world's electricity. More abstractly, the steam engine established patterns that persist: the use of fossil fuels for energy, the centralization of power generation, the integration of technology into everyday life, the expectation of continuous technological progress. We're still living in a world the steam engine helped create, even as we try to move beyond some of its limitations. The transition from steam to other power sources took most of the 20th century and is still not complete. Some steam technology remains important. The challenge now is completing the transition away from fossil fuels to sustainable energy sources, while maintaining the material prosperity that steam-powered industrialization helped create. It's a complex challenge, but not unprecedented. Societies have navigated major technological transitions before. As you drift towards sleep, imagine the gentle rhythm of a beam engine, rocking slowly up and down. Each cycle takes several seconds. The great beam rises, then falls, then rises again. It's been doing this for hours, for days, for years. The motion is steady, reliable, almost alive. The engine breathes in steam, breathes out motion. Up and down, up and down. Or imagine a steam locomotive at rest, fire banked for the night, pressure gradually falling. The metal ticks and creaks as it cools. Occasionally a safety valve lifts slightly, releasing a soft sigh of steam. The locomotive is resting, but even in rest it maintains a presence, a warmth. Tomorrow it will work again, but for now it simply is, a massive creation of iron and brass and copper, beautiful in its purpose. The history of the steam engine is, in the end, a human history. It's about people solving problems, building on each other's work, creating something larger than themselves. It's about workers tending engines, craftsmen building them, engineers designing them. It's about the societies these engines transformed and the world we inherited from the steam age. As you settle into sleep, let the story of steam surround you gently. Think of the slow accumulation of knowledge, the patience of improvement, the steady work of generations. Think of water becoming steam, of heat becoming motion, of motion becoming progress. Think of the great engines breathing their slow rhythms, working through the night, tireless and steadfast. The steam rises and disperses. The wheels turn and stop. The fires burn down to embers. But the story continues, connecting past to present, showing us where we've been and hinting at where we might go. Rest now, in the knowledge that human ingenuity can solve problems, that progress, however imperfect, is possible, that we build on the work of those who came before. The beam engine rocks gently, Up and down, slower now, its motion a lullaby. The steam whispers and sighs. The world of steam and iron fades into history, into memory, into dreams. Rest easy. Let the gentle rhythm of the engine lull you into peaceful sleep. Steam rises, invisible becoming visible, visible becoming invisible again. The cycle continues. Heat flows, work is done, and the great engines of history turn slowly in the gathering quiet. The story of steam is told. The engine room grows dark. The fires bank low. Sleep now, as the steam age sleeps, preserved in memory and museum, in the heritage railways and restored engines, in the turbines that still turn. The history is complete. The journey is done. The gentle hiss of steam, the slow rock of the beam, the distant whistle of a locomotive echoing across the years, all fade into the peaceful darkness of rest. Good night. Let the steam engine's story carry you gently into dreams.